Hello everyone. Today I will present the paper Instruction Tuning for Large Language Model, a survey. Um, so first, let's start by talking about the large language model. You have probably heard about model like GPT-3, GPT-4, and Llama. This model have completely transformed how we handle natural language tasks like generation, translation, and summarization. And we know that they call the large language model because they are quite large. For example, GPT-3 is one of the most well-known model out there, with 175 billion parameters. It has been used in everything from chatbot to virtual assistants. These models are extremely powerful because they were being trained on massive amount of text. Now here where things get interesting. While this model are quite smart, there is a bit of disconnected between how they are trained and what we expect them to do. Most of the time, large language models are trained to predict the next word in a sentence. That's great for that's great for general text generation, but not so great when we want to the model to do exact on what we ask, like write a professional email or summarize this report. Why? Because they are not trained to follow the instruction, and there's a bigger issue when we expect the model to be more of an excellent doing task the way we want them done. So here comes the problem. How to fix it? Uh, uh, the solution is something called instruction tuning. What this means that we take this big language model and fine tune them on specific example where they learn to follow instruction directly. Here is a simple example. If you give the instruction, write a thank you letter, the model will learn to generate a proper thank you letter as the output. It's like teaching the model to listen to us better. Instruction tuning helps the model bridge the gap between just predicting words and actually follow the instruction. And so why the instruction tuning is very important? Because it has three advantages: bridging the gap, and increase the controllability, increase the efficiency. Uh, First, it helps the model go beyond just predicting the word to actually doing what we want. Instruction tuning model are much and what's more, instruction tuning model are more easy to control. We can guide them to perform a specific task the way we want. Certainly, this approach allows us to adapt the model to specific domain or task without needing to train them from scratch every time and increase the efficiency. For example, OpenAI's Instructor GPT is a version of GPT-3 that has been fine-tuned to follow human instruction, and its performance much better in practice application. Now the instruction tuning is relatively new, but it's become more and more important as language model like GPT-3, GPT-4, and Panam continue to evolve. So, uh, what does the survey talk about? This survey reviews the latest research on instruction tuning. It look at how it is done, what data set are used, what the challenging we face, and what model have been successfully fine-tuned. And here is what we will cover today. Methodology, challenger, model and data set, limitation and future direction. In the methodology part, we will talk about how do we actually tune this model, what is the process, uh, and in the challenger part, we will talk about what problem come up when we do this. And for the model and dataset part, we will introduce what are the key model and dataset in this area. And for the limitation and the future direction, we will talk about what limitations exist and where can we go from here. And all right, with that overview, let's go into the first part, how instruction tuning actually works. Um, now that we have covered the basic, let's talk about how instruction tuning actually work. The process is pretty straightforward, but there are a few key steps involved. Let's break it down. First, we need a special type of data set. This isn't your standard data set. It's made up of the instruction and output pairs, where the instruction tells the model what to do, and output is the model expected to produce. After we have the data set, the model is fine-tuned, and that's what helps it to learn to follow the instruction more efficiently. The first step, the first step is to build this data set, and it's not as simple as just connect a bunch of random text. Each data point has to be very specific. In an instruction data set, each data point has three parts: the instruction, an option, input, and the output. For the instruction, this is the task we want the model to perform. For example, write a write a uh, um, blog post about machine learning, and for the option input, this could be actual information the model might need. For example, give the following outline, write a blog post about machine learning, and for the output, it is answer or the result we expect the model produce based on the instruction. So how do we build this data set? There are two main ways. The first way is data integration from existing natural language data set. We can take data set that already exists and convert them into an instruction output format. For instance, let's say we have a data set where the task is text classification. We can turn that into an instruction like classify the sentiment of the sentence and pair it with the correct sentiment as the output. For example, dataset like FLAM and P3 are built this way. They take existing labeled data and reformat it into instructions. And the second way is to generate output using large language models. The second model is a bit more automated. We can actually use existing model like GPT-3 or GPT-4 to generate output for us. We create a set of instructions, feed them into model, and let it generate the corresponding output. This is fast and in some cases even more diverse than manual approach. For example, dataset like instructor wild and self-instructor use the technique to generate large-scale instruction dataset quickly. It gets even more interesting when we look at multiple twin conversation. Instead of single instruction or output, the model has to handle a back and forth conversation. Here how that work. We can set up two versions of the model to talk to each other. One plays the role of the user, and the other plays the assistant. They take twins, generate instruction and response, creating a conversation that a model can learn from it. This approach is particularly useful for training models that need to handle tasks like customer service, where multiple conversations are the norm. Once we have a data set, the next step is fine-tune. This is where the magic happens. The model is trained in a supervised fashion, means it learns to predict the correct output for each given instruction. We take a pre-trained model like GPT-3 or Panam, and using our instruction output pairs, we teach it to follow instruction in a specific way. The model is trained to generate output step by step, learning to learning to predict one token at one time until the task is complete. The interesting part is after fine-tune, the model become much better for the instruction without needing a complete overhaul or retrain from scratch. That is what we need. So why the instruction tuning is useful? Let's quickly recap the key benefits. First, it bridges the gap. It aligns the model training with real use need. The model goes from just predicting to the natural world to actually complete the task based on human instruction. Second, it improves the controllability. You get a model that is easy to control and more predictable in its behavior. The third is the efficiency. Instead of retraining the whole model, instruction tuning is much faster. The model can quickly adapt to new task or domain with the minimal effort. Yeah. To wrap this part, here's a small summary of the instruction tuning pipeline. The step two, we build the instruction dataset by either integrating existing data or generate output using LLM. In the step four, we fine-tune the pre-trained model on this dataset, teaching it to follow instructions step by step. And finally, a model that is not only powerful but also responsive to specific user need, we will get, making it much more useful in real-world application. All right, now that we have worked through the methodology, let's move to the next part, explore something about challenge and the pitfall that come with instruction tuning. So we have seen how instruction tuning works and why it's useful, but like any technique, it's not perfect. There are some significant challenges and pitfalls that come up when tuning large language model to follow instruction. In this instruction, we will talk about three main challenges: creating high quality instruction, generalization issue, and surface level learning. Let's start with the first challenge. Build a good instruction for the model to learn from. That is actually harder than it sounds. To train a model effectively, you need a large number of high-quality instructions that cover a broad range of tasks. But how do you know if the instructions are diverse enough or they are creative enough to teach the model everything it needed to know? Here is quite challenge. Here are some specific issues. First is limited diversity. Often the instruction in this dataset only cover a small range of tasks, and they can limit the model ability to generalize to new tasks. The second is creativity. It's difficult to create instructions that push the boundary of what the model can do. Sometimes the instructions are too predictable or repetitive, which doesn't change the model enough to learn deep task understanding. If the model only thinks narrow or poorly designed instruction, it can become overly specially good at certain tasks, but not adaptable to new situations. The second challenge it is the instruction tuning model tend to perform really well on tasks they were specifically trained on. But when you ask them to do something out of this task, they often struggle. Here is a problem. If the model is trained heavily on instruction like summarize the text or classify the sentence, might do great on those tasks. But if you give a new instruction like explain the steps to solve a math problem, it might not know how to handle that because it haven't seen enough this example. This lack of generalization can be frustrating because users expect the model to handle a wide variety of tasks, but when the model overfit to specific tasks it was trained, its usefully become limited. Now the third challenge is really interesting. It's what we called surface level learning. Here's what happened. When we fine-tune this model, sometimes they learn to just a mimical pattern in the training data without really understand what they are doing. So instead of truly learning how to follow instruction, they might just be picking up on surface level. As an example, let's say the instruction is write a formal email. The model might learn to always start with dear sir or madam, but it doesn't actually understand why that is a formal way to start an email. It just learn to copy that pattern from the data. This means the model might follow instruction in form, but not necessarily in uh, substance. It's like the model is following script without really get understanding the task. While while there are the big three, there are some other small but still important issue. First is bias in data. If the instruction data is biased, the model output could also be biased. The second, it is handling complex and or unclear instruction. Sometimes instruction can be ambiguous or require reasoning across multiple steps, and the model often struggle with those. And the third is unanticipated model behavior. Even after fine-tune, model might give an unexpected or inappropriate response in certain situations. This unpredictability remains a big concern. Now you might be wondering how to fix this problem. There are still a lot of open research questions in this area. For example, how can we create a more diverse and high quality instruction data set? What technique can we use to improve generalize to new tasks? How can we teach model to understand tasks more deeply rather than just follow the pattern? These are all areas that the research are actively deploying and progress is being made, but there is still a lot we don't fully understand. To, to wrap this part, instruction tuning is a powerful tool, but it comes with its own set of challenges. Build the right data set, ensure the model journals well, and avoid surface level learning are the key challenges that need to be addressed. In the next section, we will look at the dataset and the model used for instruction tuning and how some of these challenges are being addressed. Now that we have discussed the challenges, let's move to the dataset and the model that are central to instruction tuning. We look at three types of datasets. Some of most important models that have been fine-tuned use this dataset and how this model performance in real-world application. Instruction tuning relies on high-quality dataset, and this dataset usually fall into three main categories. The first is a human craft dataset. The third is synthetic data vary destination, and the third is synthetic data vary self-improvement. Each of these has its advantage and disadvantage. So let's go to a close look. The first type is human crafted data. As the name suggests, the data is created manually by humans, which means it's typically very high quality, but also limited in this size. For example, the nature instruction dataset is a great example of human crafted data. It consists of around 193,000 instruction output pair from over 16 different tasks. Every instruction is carefully designed, and the outputs are verified to ensure that they match the instructions. Human crafted data provides the most accuracy training because every instruction is specifically tolerated to be clear and accurate. However, because it is so labor intensive, we don't usually have a large scale of this type of data set. The third type is synthetic data, generating variable base called destination. Clear how it works. We use an existing high capable model like GPT-4 to generate new data. The idea is to transfer knowledge from this teacher model to small, more efficient student model. For example, a dataset like Alapica is a great example. The researchers at Stanford use GPT-3 to generate 15,000 instruction output pair, which they then use to fine-tune a small model called NAMR. The result was a much more efficient model that performed at almost the same level as the much larger GPT-3. This method is fast and efficient. Instead of manually creating every instruction, you let the teacher model to do the heavy lifting. The downside, the quality can sometimes be lower since it's not always possible to check every output manually. The third type of dataset is synthetic data generated by model itself, what we call self-improvement. In this method, the model creates a new instruction and then tries to generate its own answer. It's like a model teaching itself. Self-instruction is the dataset built using this approach. Researchers start with a small number of manually created instructions and then feed them into model like GPT-3. The model generates new instructions based on those examples and then predict the corresponding output. The method allows for a rapid scale of dataset. You can generate a large number of instruction output pair relatively quickly. But of course, the quality might be hit or miss since there is no human oversight at every step. Now we have covered the dataset. Let's talk about models that have been fine-tuned using this dataset. There are models like sorry, these are models making headlines and transforming how we interact with AI. Here are a few examples. Instruction GPT. This is fine-tuned from GPT-3 using human-crafted dataset. This significantly improves the model ability to follow instruction and give help for accuracy answer. It's known to perform better than the base GPT-3 on tasks like question answer and providing information. And the third, it is Epica as a smaller fine-tuned version of Llama trained using distilled data from GPT-3. It's much smaller and more efficient in GPT-3, but still performance on par with it in many cases. And third, it is Wizard Llama. This model uses a multiple level system to generate a high quality instruction dataset from GPT-3, making it even more powerful. It's specifically designed for handling complex introduction and depth fill in the tasks that require detailed step-by-step reasoning. Uh, we have most focused on text-based model so far, but instructor tooling isn't limited to just text. We also have multimodal models, which can handle multiple types of input, like image, picture, or even video. Tag PMC VQA, a dataset designed for medical virtual question answer. It has over 227,000 image question pair, and it's used to train model that can look at an image like X-ray and answer question about it. This multimodal model are important for tasks that require both virtual and textual understanding. Think about application in healthcare, education, or even robotic. Being able to understand both text and image makes the model much more efficient. Let's take briefly about how we evaluate this model. After instruction tuning, model typically evaluate on how well they follow the instruction, generate accurate and relevant output, handle diversity tasks from simple summarization to complex multi-step reasoning. For example, the human evaluate benchmark is often used to test the code generation. Models like instruction GPT and Apica are evaluated based on their ability to write correct functional code in response to a specific programming prompt. Instruction tuning model like instruction GPT consistently outperforms their non-tuned counterpart on a wide range of tasks, showing significant improvement in how well they follow human instruction tuning. To summarize, instruction tuning relies on three main types of data set: human craft, synthetic via destination, and synthetic via well, self-improvement. Model like Instructor GPT, Applica, and Wizard LM have been fine-tuned using this dataset and have shown significant improvement in their ability to follow human instruction. Instruction tuning is moving into multimodal domain, opening up exciting new possibility for tasks like combined text, imaging, and other type of data. In this section, we will look at some of in the next section we will look at some of the challenging this model face and what a future research is headed. Now that we have covered how instruction tuning works, the data set, the model, let's talk about some of the limitations that have come up around this technique. While instruction tuning has shown a lot of promise, it's not without its limitation. In this section, we will explore some of the key limitations and what researchers are working on to address this issue. One of the biggest limitation is the model trained with instruction tuning tend to overfit to a task they have seen during training. It means that the model gets really good at specific task in the instruction dataset, but struggle when you ask it to do something slightly different. If the model trained on summarize articles, it might good at it, but if you ask to summarize a technical research paper, it may struggle because it haven't seen many examples like that during training. Overfitting limits the model generation ability. In real world, we want to a model can handle a broad range of tasks, not just the one they are trained on. So this is what we should solve. The first challenge and limitation we need to address. The second major limitation is something we have touched on earlier. Uh, 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 Surface level learning. In many cases, instruction tuning model appear to follow instruction, but they do but they do so at a surface level. They may mimic the format of response, but they don't fully answer the task itself. If you ask a model to generate a formal email, it might start with a dear sir and with sincerely, uh, but it might fail to introduce important detail or the context in the email itself. Surface level enhance means that the model isn't really understand the task deeply. It's just following a pattern. This makes the model less reliable for complex tasks that require more than just a template response. Another concern is the dataset used for instruction tuning can sometimes carry bias. Since not all of the data come from the internet or other human source, it can reflect so social bias related to gender, race, or even political views. Uh, for example, if the data contains certain type of task of perspective, the model may end up giving bias on or unbalanced response. That is especially problem in sensitive area like hearing, legend advice, or even healthcare. Models that carry bias can produce unfair or inaccurate results, which can have serious consequences, especially when they are used in decision-making systems. Another challenge is how this model deals with ambiguous or multi-step tasks. Instruction tuning model often struggle with instructions that require reasoning, problem solving, or decision making across multiple steps. Let's say you ask the model explain how to write a research paper and include the step for submit it to a journal. The model might provide a general answer, but fail to give a comprehensive breakdown because it struggles with a task that spans multiple steps or require deep reasoning. In real-world application, users are often giving complex multi-step instructions. If model cannot handle this well, they become less useful for tasks that require detailed guidance. Now that we have looked at the limitation, let's talk about where instruction tuning is headed. There are some exciting research directions that aim to address this issue and improve the overall performance. Oh, uh, sorry. Now that we have looked at the limitation, let's talk about where instruction tuning is headed. There are some exciting research directions that aim to address this issue and improve the overall performance in instruction tuned model. One of the biggest area of focus is improving the model ability to generate to new tasks. Researchers are looking for ways to make problem more reflexible and adaptable. By creating more diverse and creative dataset that explores the models to a wide range of tasks. Using meta-learning technique where the model learn how to learn new tasks with minimal data, which could help them generate better to understand tasks. If we can improve generalization, model will become more reliable across a variety of tasks, making them much more useful in real-world application. And another key research area is helping model move beyond the surface never learning to develop a deeper understanding of tasks by focusing on models that can perform the reasoning and multi-step problem solving rather than just follow instruction in a uh, meaningful way. Techniques like chain thought promoting are being explored, where models are trained to break down complex instructions into uh, into a series of small steps, improving their ability to handle more small tasks. We need models that can handle complex tasks with depth and flexibility, not just produce predictable pattern-based output. Addressing the issue bias in instruction data set is another priority. There is ongoing research into how we can identify and reduce bias in both the training data and the model response. By editing data set to better understanding where the bias are coming from and design technical to filter all biased data, developing fairness algorithm that can adjust the model output to be more balanced and unbiased across different groups. Bias in AI model can lead to harmful outcomes, especially when they are used in areas like hiring, healthcare, or no inference. Reducing bias is important to making AI system more fair and equitable. Nothing research are working on improving the model handles ambiguous or multi-step tasks. This involves training model to better understand tasks that aren't clearly defined or require multiple decisions. By incorporating more complex multi-step tasks like into training data using technical like self-reflection, where models are trained to recognize when they don't fully understand the task and ask for clarify or break it down into small parts, handle handle ambiguity and complex tasks is key for model to be useful in real-world application where instructions aren't always predicted clear. Instruction tuning is a powerful technical, but it still faces challenges like overfitting surfaces, learning bias, and struggling with complex tasks. The future of instruction tuning is focused on better generalization, deep understanding, reducing bias, and improving the model's ability to handle complex instruction. These are the areas where we can expect to see significant advance in coming years, making instruction tuning model even more robotic and useful. To close up, instruction tuning has already transformed the way we interact with large language model, making them more responsive and accountable. But we still just sketching the surface. The research community is actively working to solve the current challenge, and the progress we see in both is both exciting and impactful. That's all. Thank you.